Okay, so we're going to build a definition for what we're going to call a definite integral. And this is where we start the process of integration. So we're going to let go of derivatives and all of this for a little bit and just start with some geometry. Okay, so here's my coordinate axis, and I have some function. We're going to call that f of x hanging out above it. And we're going to drop down a value here a and a value here b. And we're going to look at the area of this region right there. And we're going to say that that area is going to be defined as the definite integral from a to b of f of x dx. Okay, so this is literally the definition. Okay, so don't make anything more out of this than it really is. It's just notation that means it's the area of that region. Okay, so a couple of notes. One, when f of x is less than 0, then the integral from a to b of f of x dx is also less than 0. So if the curve is below the x-axis, there it is, then we consider the integral to be negative. Another quick note that's important to catch here is that if I change the bounds of integration, so instead of writing a to b, I write b to a. If I take the negative of that, that's going to be the integral from a to b of f of x dx. So if I read these from right to left instead of left to right, I'm going to get a negation. Okay, so that's pretty simple. That's pretty straightforward. That is the definition of a definite integral. Now we're going to look at a couple of quick examples of finding some of these values where I don't need to do a derivative or an antiderivative or anything. All right, so let's take an example. Let's say f of x is equal to 4. It's a constant, right? So if I think about this graph, right? So here's my x-axis, here's my y-axis, here's the value 4. This is the line that is f of x is equal to 4, right? Let's say I want the integral from 1 to 6 of 4 dx. Well, then I put my line down here at 1. I put my other line down here at 6. And that integral is this area right here. Well, the width of that integral, or that area, is 5. Its height is 4. And 5 times 4, lo and behold, is 20. There we go. I have calculated an integral by simply doing multiplication. All right, so let's look at another example. What if I draw f of x in such a way that it starts down here at 1, it goes up, and it comes back down here to 7, and its maximum height is 5, right? So though it may not look like it, I want it straight segments here, okay? So this is like a triangle, right? All right, so there's my triangle. That's really ugly. Let's fix that a little. Okay, so it starts at 1, comes up, comes down to 7, has a height of 5. It's a triangle. Okay, so this is f of x. It would be like a by parts function, right? So the integral from 1 to 7 of f of x dx here would be 1/2, and the base of this thing is 6, right? The height of this thing is 5, and well, that's half of 30, which is 15. All right, so there we go. It's just the area of the triangle right here. All right, not too bad. Let's do one more. All right, so let's get a little tricky here. Let's put the curve below the axis, right? And we're going to say that this curve is f of x is equal to negative the square root of x squared minus 9. All right, so this is essentially going to strike down here at negative 3 and 3, and I have the origin 0 here, and I want the integral from 0 to 3 of f of x dx. Well, this is a quarter of a circle that has a radius of 3. So the area of the circle is 9 pi, which means the area of this piece is going to be 9/4 pi, but it's below the line, so this is going to be -9/4 pi. And there you go. Yet another definite integral. No tricky stuff with derivatives or antiderivatives or anything like that. Just getting the basic idea down here. So that's it. There you go. And we'll talk about this more in next class.